So in this question, we have a projectile thrown upward. The ball is thrown, the stone is thrown up and comes back down. And again, it doesn't really take this path. It's just we're translating it a little along the x-axis so that we can see the motion. So this is a great opportunity to use our average velocity table to allow us to get estimates and see what's going on here in terms of time. We'll just do a few seconds. And if we need more, we can fill it in. So time 0, 1, 2, 3, and the instantaneous velocity, average velocity, and the change in height, delta z. So initially we know the velocity is 8, and it changes by -10, so that becomes -2, -12, -22. Average velocity is meaningless at time 0. 8 plus a -2 is +6, divided by 2 is 3, and 8 plus a -12 is -4, divided by 2 is -2, and we get -7, like so. And we know the average, or the change in position vertically, is equal to the average velocity times the time. So 0, 3, -4, -21. So we'll just leave it at that for now. So it leaves our hand with 8 meters per second. We're using normal G, ignoring air resistance, which is the standard unless we're told otherwise. We want to know the maximum height. Well, the maximum height, the velocity equals 0. So let's get an estimate on that. We'll look in our table and we'll try to find out when the average velocity reaches 0. And we can see that must happen between 0 and 1 seconds. To get to -2 from +8, you must cross 0. So we have a 0 velocity in there like that. And that means the maximum height, we see that it's 0 in the beginning and 3 at time 1. Well, at time 1, it's already moving downward. So that means its highest point was before it got to 1 second, which means it was higher than 3 meters. So the maximum height is greater than 3 meters. So there's some things we want to say. If we're taking notes on the side, we want to say that the velocity equals 0 at the max height. I want to show the raters we understand. And so we solve for that. V equals AT plus V0. So that's when 0 equal -10t plus 8. And so 10t equals 8, and t equals 0.8 seconds. So now we need to find the delta z. And I'm always recommending that we start out with average velocity. So average velocity is delta z over delta t. So therefore, delta z would be average velocity times the change in time. Now we know the time is 0.8 seconds. We just don't know the velocity. Well, we have our other average velocity formula, which is v plus v0 over 2, when the acceleration is constant, which it is. And so the average velocity then is the final velocity, 0 plus 8 over 2. So the average velocity is 4 meters per second. So we have 4 times 0.8, which is 3.2 meters. Now, 3.2, we check it against our table. Yes, it should be greater than 3.2 meters. So we have our answer. Now, that's the one way we could do this. We could also do the second part of this after we have the time using our position formula. So we want to know when z is a max and the acceleration is -10. The time is 0.8 seconds. Initial velocity is 8. Time is 0.8, and initial position is 0. So that gives us -5 times 3.24 plus 6.4. And that then gives us, I made a mistake here. That is 1/2 -10 times 0.8 squared, which is -5 times 0.64, which is -3.24 plus 6.4. That's -3.2, excuse me, not -3.24. Thinking back to a previous problem, -3.2, and that then gives us plus 3.2 meters. So we can see that after we have the time, there's two ways we could go about getting that 3.2 meters. The question is, which way do we want to show? So we definitely want to put this over here. We need to put this over here. And we could choose either of these. It doesn't matter, whichever is going to be easiest for us that we put over here in a nice, neat, orderly fashion so the rater can find it. Second question, the time it takes to reach its maximum height. Well, we already have that, so we could write that there. And then lastly, the time it takes to hit the sea, we know is 3 seconds. Now, what's interesting is we used our average velocity table, and at 3 seconds, we know the delta z is minus 21 from our table. Because it's 3.0, we know exactly on the spot that it's minus 21. We have our answer already. But we have to find a way to solve this in a different way to show it, because the average velocity table is not going to cut it, because that's a trial and error. So what we want to do is diagram this picture a little bit more detailed way. So we've got our projectile going up like this and coming down. Now, what I want to do is take a look at what's going on with the times, because we know it hits at 3 seconds. Well, we know it takes 0.8 to get to the top. We also know it takes 0.8 to come back to the same height. So that means that to return to the same height is 1.6 seconds, which means the last part of this is 1.4 seconds. We also know the initial velocity is plus 8, and we know the velocity here then must be minus 8. So we could use our z equation to solve for this. And so z equals 1/2 at squared plus v0t plus z0. And we know the acceleration is minus 10. And if we're going to start here from this location, we know the time is 1.4 seconds. And the initial velocity is minus 8 times 1.4 seconds. And when we do that all out on our calculator, we get minus 21 meters. So it checks against the table. Now, had we done this differently, had we started from the very beginning back here, z equals 1/2 at squared plus v0t plus z0, well, the acceleration is minus 10. The total time is 3. The initial velocity is 8. Time is 3, and the z0 is 0. So z is minus 5 times 9 plus 24. So this is minus 45 plus 24, and you can see is minus 21. So it doesn't matter which way we set this up. We are going to get the same answer, and we have confidence it's correct because we already had the answer in our average velocity table. So we got multiple checks built in. We're going to get all of our points for this. So if we use this approach, we should include this diagram. If we use this approach, we can just use the whole thing like so. And that's how we do question A9.